Hey all, welcome back and welcome to Chapter 6. We're going to look at just the beginning of Chapter 6 here, talking about friction force in this video, and then we'll continue on to some additional types of forces, drag force, gravitational force, and so on, with the remainder of Chapter 6 a little bit later. But for now, let's jump in and talk about friction. That's an example of friction. Anyway, sorry. Okay, so what is friction? Well, it's a force that opposes motion when two objects are sliding along one another's surfaces or along some surface of contact. So, as I mentioned just a moment ago with my hands, if I push this top hand against the bottom hand, there will be a friction force opposing my direction of motion. Or if I have my cell phone sitting here on my hand, how does it stay on my hand? Well, there's a friction force opposing its natural direction of motion. If there's no friction, it would slide right off of my hand because of the angle and because of gravity. But there's some friction between my hand and the phone opposing that gravitational component of force making the phone want to go down my hand. So that is the force of friction, and we see it all over the place. In fact, if you've walked anywhere today, you've used friction force because it's the force of friction between your feet and the ground that actually propels you forward. If you've driven anywhere in the last week, it's the friction force between your tires and the road that propels the car forward. Without friction force, you would not be able to walk anywhere, and you would not be able to drive in the way that we typically do. But the question is, what gives rise to friction force? Why does this exist? Why is there this natural opposition force every time two surfaces are being attempted to slide against one another, or sliding one on top of the other is the way you might see it more typically, but you could slide the bottom object as well. And what gives rise to this force is the fact that no surface is perfectly smooth. Even if you look at something like, here's, my calculator, the back of my calculator, it looks pretty smooth, right? Well, if you were to zoom in at a microscopic level, you would not see this perfect apparent smoothness. Instead, you would see little bumps along the edge, as you see in this kind of zoomed in picture of these two blocks here. This roughness, this surface roughness, is what gives rise to friction force, because these little points that you see here can get caught on one another as you try to drag one surface on top of another. And as those little points get caught, they catch up and they resist that sliding action, and so that gives rise to the force of friction. So force of friction is ultimately caused by small imperfections in a given surface. The smoother the surface, the less of these imperfections there are, the less friction force you'll experience. That's why walking on ice or something like that, you're a lot more likely to slip and fall, because there's not nearly as much friction as there is on something like concrete, which has a lot more surface roughness to it. So that is kind of a brief introduction to the idea of friction. Now let's dive into it in more detail. So when we talk about friction, you need to understand that there's actually two kind of categories of friction that we're going to talk about. We're going to talk first about what's known as static friction, and then we're going to also talk about what's known as kinetic friction. And as the names imply, static force of friction is the force of friction when something is static, not moving. Kinetic force of friction is the force of friction that something exerts when it is moving. And these are different forces because you can have different magnitudes of static friction versus kinetic friction. A lot of times, as you'll see here shortly, in almost all cases, static force of friction, when at its maximum possible value, is larger than kinetic friction. And you see this in day-to-day life when you try to push something. Say, for example, you're helping a friend move and you're trying to get their refrigerator moving out of its little slot so that you can load it onto a dolly and roll it into the truck. When you first try to get that fridge moving, it's actually harder to start its motion than it is to keep it moving, and that's because there's a larger amount of static friction, or a larger, let me rephrase that, there's a larger maximum possible static friction than there is kinetic friction. But the key with static friction, something that's a little confusing about it, is it actually has a range. Static force of friction can have a value anywhere from 0 up to some maximum value. And you'll see that in the equation here shortly, but let me explain a little bit. So let's go back to my calculator sitting on my hand. Here's my calculator sitting on my hand. Right now, it's on a level flat surface, so the static force of friction right now is 0 because friction resists movement, resists even attempted movement. So since there's no force pushing this from one side or the other, there's no need for static force of friction to resist any motion. So right now the force of friction is 0. Now, if I started pushing, let's say I push on the end over here with 1 Newton of force. Guess what the static force of friction is? Well, we know it's in equilibrium. Its net force is 0 since it's not moving. So if I'm pushing with 1 Newton of force in this direction, then static force of friction must be the opposite way, also equal to 1 Newton. If I push with 2 Newtons of force, guess what the friction force is equal to? It's still static, and it's equal to 2 Newtons. I push with 3 Newtons. I push with 4, static force of friction is 4 Newtons. It's only going to resist as much as it has to. Now, if I get and push this more than that maximum possible static force of friction that you can see labeled down here, F sub S for static force of friction, and then maximum. Once I reach the maximum possible static force of friction and go just 0.1 newtons beyond that, then your object will begin to slide. The static force of friction fails and it begins moving, and you will then have kinetic friction. Okay, so let's say that between this calculator in my hand, the maximum possible static force of friction is, say, 10 newtons. All right, if I push with 1 Newton, again, we have 1 Newton of static friction opposing it. If I push with 9 newtons of force, all right, we'll have 9 newtons of static friction opposing it. The moment I reach 10.1 newtons, though, boom, it begins to slide. It will move because static force of friction is weaker than the applied force, and so there's a net force, and as we learned last chapter, we know when there's a net force, there will be an acceleration. So that's static force of friction. Let me show you kind of this idea that I'm describing and what it looks like graphically. All right, if we were to graph, here is a situation where, let's say we have my calculator again. On the x-axis is the amount of applied force being applied to it, okay? And on the y-axis is the force of friction, all right? So what we see, if zero force of friction, or sorry, if zero force is applied on the x-axis right here, then there's going to be 0 friction. If we move up a little bit, like we were talking about before, to 1 Newton of force, then friction will also be 1 Newton, and it'll again still be static. If we go up to 5 newtons of force applied, then we still have a static 5 Newton force. All the way up until you reach that maximum static friction, which is, in my example I just made up for the calculator, would be 10 newtons worth of force. That's represented by this point on the graph right here. Once you reach that maximum, you go the tiniest bit beyond that with the applied force, and boom, guess what? Your object begins to move, and now you have kinetic friction. And as I mentioned before, kinetic friction is going to be a constant value and is almost always, or at least typically, is less than the maximum possible static force of friction. So in this case, with my example, maybe this maximum was 10 newtons, the amount it takes to push my calculator to get it moving. And then down here, the kinetic would have been something like maybe 9 newtons of force. Okay? So keep in mind, kinetic force of friction at typical speeds, at least for all of our applications, we're going to assume kinetic force of friction is approximately constant no matter what the applied force is. Static force of friction, on the other hand, is only going to be equal to whatever is required to resist the forward motion up until some maximum, at which point it can no longer resist forward motion and your block will begin to slide. Okay, so hopefully this makes sense. If you're curious and you look at this graph and you say, wait a second, you just said kinetic force of friction is approximately constant, and I look at this and it's bouncing up and down a little bit. Well, any guesses? What would you guys think? Why would this be bouncing around like this? Why is it not a perfect straight line if we're saying it's more or less consistent? Well, the reason for that, and hopefully you came up with a guess on your own, but the reason for that is because of surface roughness not always being perfectly consistent. Okay, this bounces up and down because you hit more rough patches and less rough patches on your two surfaces. So again, going with the calculator on the hand example, as I'm pushing it along my hand, there's parts of my hand that might be a little sweatier, a little stickier for some reason. I ate a little too many gummy bears at lunch or something, and it's making my hand a little more sticky in one spot than the other. That would cause a slightly higher kinetic friction. Once it moved past that, then it would be a little bit lower, and so it bounces around based on random surface roughness and kind of stickiness in a sense. Okay, so how do we quantify these two things? Well, first of all, as I mentioned, static force of friction is going to be less than or equal to some maximum value. So it can range anywhere from 0 up to some maximum value. The way that we quantify what that maximum value is, well, it's equal to what's known as mu sub s, also known as the coefficient of static friction, multiplied by the normal force. All right, so it's really amazingly simple. Friction force, the maximum possible static friction force, is just dependent on this coefficient as well as the normal force. And this coefficient of friction is a number, a ratio actually, so it has no units, but it's a number representing how rough two surfaces are when they come in contact with one another. So that's something that's going to be experimentally determined, and you'll either have to calculate it or I'll give it to you depending on the situation. But there's known values for these coefficients, which I'll show you in a table here in just a second. But keep in mind, a lot of people get confused by this. Static force of friction is always going to be less than or equal to this maximum value. And so when you're thinking about this, if I give you a problem and let's say, you know, again, just because I have it here, we're going to talk about my calculator on my hand again. But if I were to ask you, you know, okay, how much force is required to just barely get my calculator start moving? You might wonder, are we talking about static or kinetic friction? Anytime you hear a problem where it talks about just getting started to move, that's going to be talking about a situation where you want to set your static force of friction equal to its maximum possible value and then calculate based on that, okay? So that's the static coefficient of, or static force of friction. The kinetic force of friction now is when we are in motion, your object is actually moving, and since we're going to define it as being more or less consistent or constant for now, we're going to define we're going to define kinetic force of friction as being equal to the coefficient of kinetic friction, again represented by the Greek letter mu and then the subscript k for kinetic, multiplied by the normal force. All right, so keep in mind, again, the only two things this depends on is this coefficient and the normal force. So how can you affect or change friction? Well, it's not dependent on the orientation of the object. Any direction that I place my calculator on my hand, in theory, should exhibit about the same amount of friction. If the surface roughness is the same on the top as the side, the normal force is just equal to the weight of my calculator. So no matter what, you're going to have the same force of friction under any orientation. The only way I could possibly change the force of friction is if I were to angle my hand and now I have a different normal force, or if I were to take something else like my cell phone, place it on top of the calculator, I now increase the normal force and therefore would change the force of friction. Okay? So that's a brief introduction to the idea of force of friction. Here's a table that I found with just a few examples of coefficients of friction. So in this column you see static coefficients of friction, and in this column you see kinetic coefficients of friction. And as I said, in almost all cases, your static coefficient of friction is larger than your kinetic force of friction. The only exception in this table is when you have Teflon on Teflon, you can see the coefficient of frictions are approximately equal to one another. But in all other cases, the static is larger. You can see there's some situations where you have very high coefficients of friction, like rubber on dry concrete over here, all right? And you have some situations with very low coefficients of friction, like steel on ice. This is a very smooth steel. Ice on ice, not too dissimilar from a hockey puck or something. And then you can see Teflon as an extremely low coefficient of friction. So there's just some examples of what these coefficients would look like. Again, you'll either be given these or you'll be given all the information so that you can solve for them. They're experimentally determined values. When you get to your final project, you might have to experimentally determine them on your own, but in all other cases, you'll be given them or solve for them. So let's talk about a couple examples really quickly here. All right, so here's a sled. Here's somebody who runs, jumps on a sled. They jump on the sled on this flat surface, moving with an initial speed of 4 meters per second, and they slide a distance, x, labeled here, and eventually come to stop. What is it that stops them? Well, it's their friction force. What type of friction is it? Well, they were moving during that time, so it's a kinetic force of friction that's causing them to slow down. So based on this information given to you here, I could actually ask you to solve for that kinetic force of friction. So let's say, and there's a couple different ways you could do this, but the way I'm going to do it is I'm going to tell you that this person has a mass of 40 kilograms, the person and the sled together, and if we're looking at a very well-polished sled on very icy snow, let's say the coefficient of friction, kinetic coefficient of friction is 0.05. What is the total frictional force? Pause the video, calculate it for me real quick. So hopefully you did a quick calculation, and what you should find is the force of kinetic friction, which we know is equal to the kinetic coefficient multiplied by the normal force. So that's what it's going to be equal to. And now, since we're on a level flat surface, we look at our free body diagram here, and we can see that our normal force is just going to be equal and opposite to our weight force. So the force of kinetic friction is equal to the coefficient multiplied by mass and multiplied by gravity. So you do the math, you plug and chug, and boy howdy, boom, you should get a box worthy approximately 20 newtons of frictional force being experienced by the child on the sled. So that wraps up the end of the first section of Chapter 6 about frictional forces. I have a pretty tricky example problem for you guys that I'm going to be doing in a separate video, so be sure to check that out next.